Okay, so even if you've done all of this correct, right? Then you got to put it in the calculator correctly. So do you have a calculator available for us today?
Yeah. So
All right.
just be like 74 times 3 times 22.4 divided by 2. So 22.2.
3, maybe round up to 3.
Oh yeah, 3.
And then I noticed that it looked like some of the answers might be on
Yeah.
there.
Mhm.
Oh, and that is the answer. Great.
Yeah.
Okay. Well, so at least we're consistent with the
Yeah.
worksheet. All right, number 2. Looks like you've made an attempt here at writing the equation. How confident are you in whether this is correct or not? I have no idea, by the way.
Yeah, I don't know because I think I wrote it out and then it looks like, yeah, and then I tried to balance it and I think I did it right, but then I had solved it and it wasn't right. So
That suggests something is amiss, either the original equation or not. So aluminum nitrate reacts with excess lithium carbonate. All right, what is the theoretical yield of the precipitate? Which I actually don't know what that is. We'll figure that out. All right, let me go out to the wonderful internet here and see what I can find here. Aluminum nitrate. All right, so that's AlNO3 3. So somewhere along the way, you learn that nitrate is something. Aluminum is +3, I want to say. I don't know. Let me go look. I don't know how important this is for you, but aluminum is +3. And I believe the nitrate is -1. That's why you need 3 of them here. So somewhere you learn about nitrate, nitride,
yeah.
fate, fide. I don't know, all those eights and ides. And then lithium carbonate. So kind of the same deal here. Carbonate is Li2, and this should be CO3. Good. Okay, that looks good. And then it's like, all right, well, how do we know that? What's the charge of lithium? +1. Okay, so that looks good. LiNO3, because lithium's +1, NO3 is going to be -1. And then aluminum is +3. So I think this is off. I think it should be Al
Yeah.
Li3. I'm not being critical. I'm just trying to like make sense of it myself. I would really struggle with this as well. So, all right. So we have aluminum nitrate reacting with excess lithium carbonate. All right. Al2NO3 plus Li2CO3. Okay, we got that. And then do we have the products correct? LiNO3. Got that. And then Al2. Okay, sorry. So it's I messed this up here. It's Al, and then we have the carbonate here, CO3, and then you've got 2 of these and 3 of these. All right, let me just start over here. There's just so much going on. AlNO3 3 plus Li2 CO2 CO3 produces Li, make sure we don't need that, NO3 plus Al2 CO3 3. Then you have to balance this, and it looks like, just to save some time here, those are the coefficients needed.
All right.
So I can the way to do this, if we're going to do this like correctly, is you got to go figure out the charge of aluminum, the charge of nitrate, the charge of lithium, the charge of carbonate, piece them together on each side. Because it's a double replacement, piece the new ones together with the right charges and coefficients, then balance. Okay. All right. When 120 grams of aluminum nitrate reacts, so we're starting out with 120 grams of AlNO3, and you need the molar mass of that.
Mhm.
And let me go find a molar mass calculator. I really like this one from Lentech. I can send you a link to that in the chat here in case you don't have it. Basically, just type it the way you AlNO3 calculate. That's a big one. 2358 grams. Okay. And that's 1 mole
Mhm.
AlNO3. Okay. And then we need the mole conversion. So what I don't know is the precipitate. Do you know which one is the precipitate over here, the lithium nitrate or the aluminum carbonate?
I think
All right, the precipitant of the reaction. That's not going to work. It wants us to compare this other stuff.
yeah, I have no idea what the precipitant is. My teacher is like really bad at explaining.
So the general way to figure it out is the one that is insoluble in water. Okay, and it's like, so one of these is insoluble in water, and I don't know which one it is that they at the moment here. So let me go check another thing. Precipitant product. Uh, hmm. The math really isn't that hard once we know these things. They really done a good job here of making this difficult by not telling you which one it is. So like one way to do it is to just do it for both and then figure out which one it was based on that, but that's pretty hard. So or it's just more work. So I'm not gonna be able to figure it out here. So let's just say that the first one is the precipitate for the moment. There's 1 mole AlNO3 for 6 moles LiNO3, and then you have to multiply by the molar mass. So 1 mole LiNO3, and let's get that here. And if this is wrong, we know it's the other one, and then we can go from there. So this one is 69, we'll say, grams. So if this is wrong, we'll put a 1 here for the 1 mole Al2CO33, and we'll change that. But since we have the answers, maybe this will work.
Okay.
So I got 21 for that. And then we know that the answer is 65.9. So if we put a 1 here instead, so put a 1 there instead, and we get rid of those from the moment. We change this number to Al2CO33. Which is 234. .9 grams. theoretical yield of the precipitate. So neither of those look correct.
Yeah.
Is it possible this is wrong? AlNO33.
Yeah, let me look. So AI is, or yeah, AL is 27, oxygen is 16, and then
Yeah, this is way off. I don't know what happened there.
it's
So let me change that in the calculations here. Rough start to the day here.
57, I think.
213, 134, or and we know the answer is 65.9 grams.
Yeah.
Doesn't seem right. Neither of these are working out.
Let me-
120 grams, 33, 1 mole to 1 mole, or 1 mole to 234, or 69, 69. It could be a balancing issue too. I would recommend we move on to another problem since this one's going so poorly.
We can do the next one, maybe.
Yeah, I apologize. There's just some questions that need to be answered to get the information here. All right, combustion here. This should go a little better. Are you in like an honors chemistry class where you gonna go the extra mile here a little bit, or?
Well, it's like it's weird. My school, like, so we have for sophomore year, which I'm in, we have like two science classes, honors chemistry and physical science, and there is no like regular chemistry. So if you pass like algebra with like an A or a B, they put you in chemistry for some reason, and it's honors. So like you have to do
I
honors.
see. Yeah, because you're getting the harder stuff where you're gonna write the equation. All right, so I'm gonna do the better thing here. I'm just gonna go look for the combustion reaction of pentane. Why react with? So having the equation here would be really, really helpful.
Yeah.
Oxygen or gas required to fully react with 80 grams of pentane. So it's like you've got here, but then, what does that become? My guess is it's CO2 plus H2O. Does that sound familiar?
Yeah, I think that's what
Okay. And so now we can attempt to try and balance it. The H is you'd put a 6 there. That gives you 6 O's there and 8 there. So that would be a 4, but then 5. So the 5 there, you put a 5 there, that's 10. 10 and 6, 16. So maybe an 8. So let's just double check it again. 16 O's, 10 and 6, 12 of those, 5 C's. Okay, maybe we got it. How many liters of oxygen required to fully react with 80 grams? So you start with 80 grams of C5H12. Always go to the molar mass, C5H12 grams in 1 mole of C5H12. I got 72-ish right there. And then mole conversion. So 1 mole C5H12, but they want how many liters of oxygen gas are required. So that's the 1 mole C5H12 to the 8 moles of O2. And then we have to convert 1 mole O2 to 22.4 liters O2. And then we hope, we really hope that that works out here.
So Yeah, it worked for me.
Okay, so I get like 199 liters. Okay, we're making, 2 out of 3 ain't bad. Famous musician, I think once said that. So, let's keep going here. Uh, all right, so is the idea of limiting an excess reactant at all? Would you like some clarity on that, or maybe we'll see it through this problem here? But do you have kind of a general idea of what limiting an excess refers to?
Yeah, I do.
Okay. All right, so we have iron 3
Mhm.
combination between 6 grams of iron and oxygen. Okay, Fe plus O2 becomes Fe2O3. We saw that earlier in the decomposition, so I kind of feel like it's okay. Two irons, 4 irons, 6 O's on the right, so there's 3 there, and then we can proceed. So you're starting out with 60 grams of Fe. Oh, and okay, how much excess reactant is left? So in this problem here,
Mhm.
you say you presume, you say, okay, let me first start out and say, all right, I hope, if let's just say I can consume all of this, how
Mhm.
much of this will I produce on the right? So you're like really optimistic. And I always draw an analogy to baking or cooking when you do this, but it's like, I hope I can use all this up. Let's see how much I can actually produce. So I think you said earlier, iron is like 55.8 grams
Yeah.
in 1 mole. Then you do your mole conversion here, 4 moles Fe to 2 moles of Fe2O3. Now, a lot of students here will go to grams, but you don't need grams. You can just do it in moles. You just want to know how many moles of this you're going to produce. Okay, so we get that number. Please double check me because this is an important calculation here.
I got the same.
Awesome. So now you do the same thing for the other one. You're like, all right, let's just, forget about what we did there. Let's hope we have enough. If we use all of the other one, the 660.2 times 10 to the 23rd molecules times, excuse me, 6.022 times 10 to the 23rd molecules in 1 mole of O2. I should have no O2 here, O2 here, times 3 moles O2. So you always use the coefficients in this.
Yeah.
The 2 moles Fe2O3. So you do that calculation and you look and you see, well, we'll answer here in a moment. So get those numbers.
Um,
Did you get like 6.66?
yeah.
Okay, so here's what you should be looking at. You should say, you're looking for the smaller one. Okay, so the smaller one here tells you the limiting one.
Yeah.
And the reason is the it's limiting is because you can't make as much as you would as with the other one. So the other one is now considered in excess. Now it's not that these numbers are in excess. They tell you that the iron, in this case, the iron is the limiting one, and the O2 is the excess. Like you've got too much O2 or not enough iron in that scenario. So now, how much excess reactant is left? Okay, so we figured out which one's limiting, how much excess reactant is left. So there's probably a faster way to do this, but what you do is figure out when it says how much, I assume that's in grams.
Mhm.
What do you think? Does that mean grams?
I think so.
Okay, so we figure out how do we want to do this? We figure out how many grams we actually needed from this number. So you start with the limiting one and you say, okay, I have 0.538 moles of the Fe2O3. How many, and we're going backwards now. It's like, how many grams of oxygen did you really need?
Mhm.
So to do that, you got to again use the mole conversion. You got the coefficient 2 moles Fe2O3 to 3 moles O2. So you're going backwards. And then 1 mole O2 is 32 grams of O2. So basically what you're saying is like to produce 0.538 moles, how many grams of O2 did I actually need? And this will give that number there.
Mhm.
There might be a faster way if you're chemistry, ninja, black belt, not me. I'm pretty weak here, but we know that we need 24.82 grams of O2. Now this problem is further challenged because we don't actually know how many grams we started with. So we have to use this molecules information to figure out how many grams of oxygen we started with.
Mhm.
Okay. So to do that, you take that 60.2 times 10 to the 23rd divided by Avogadro's number, 6.022 times 10 to the 23rd. And that's 1 mole. And then 1 mole of O2, this is all O2, excuse me, is 32 grams of O2. So basically you have to kind of go back to the original and figure out, well, how much did
Mhm.
we actually have? And wow. So you end up having, you initially had like 320 grams,
Mhm.
but you only needed 25.82. So that's why it's an excess, because and there's really a strong analogy to cooking when you have like extra ingredients or
Mhm.
not enough of something. So the excess here is the 320 minus the 25.82. And I guess I hadn't checked these. Are these checking out here on
I think
page 1?
we'll see.
Oh, they do their excess in the 10 to the 23rd is the the atoms. So I guess we need to do that. Wow, that's pretty tough. Okay. Just for the sake of time, I just suggest we maybe do another problem here but the idea would be you'd have to convert.
Yeah, no, I get that.
Okay. Yeah. All right. 5. I keep thinking, well, maybe there'll be like an easy one here and
No.
not. Um, uh, all right. So again, the way to do this is to go to your periodic table and look up calcium and know where calcium is. Calcium is well, calcium is +2.
Yeah.
Okay. And nickel 2 is +2. And then we got nickel 2 chloride. So I don't remember what the chloride does, but that's kind of a thing. So it's Ca plus nickel and then chloride. So I guess Cl. Cl is -1. So I believe there'd be 2 of those. Does that make
Yeah.
sense? Okay. All right. And then it's a reaction. So we have to figure out what this is producing. So we presume here it becomes calcium chloride, which would be CaCl2 plus nickel by itself. That's sort of how I think through these. In this case, there's no coefficients. Excuse me. So let me just take a look here, because everything is based off this.
Mhm.
All right, so calcium reaction. You know, there are some product calculators out there,
Mhm.
so that would be something to consider. I can't say for sure this is right, but
If it's already balanced, you just do like one as the
yeah,
code.
yeah, it's quite straightforward in this case. But I'm really bothered by the fact that like this, because the other ones have been so much easier than this.
Yeah.
Um, but let's keep going here. 120 grams of calcium, 50 grams of nickel. What is the limiting reactant? So you have to predict how much, like you go in each direction, say, okay, calcium to like CaCl2 or calcium to Ni, either one. That's why it's so important to have this thing balanced.
Mhm.
Oh, and but they do say if 42 grams of nickel are actually produced, that suggests maybe we just go to nickel.
Mhm.
So you basically have to go Ca to Ni and then NiCl2 to Ni and see which one is the smallest.
Mhm.
So let me just look at the answers real quick. It didn't seem like they were giving you that many numbers. Like there's 1, 2, 3, 4 questions, and it only gives you like 2 answers.
Yeah.
Okay, which 2 do we think it's giving you?
Um,
Oh boy. Okay. Well, so we got 120 grams of calcium times, we're going to find the mass of calcium, which is 40. So there's 40 grams Ca and 1 mole. And we know it's 1 mole to 1 mole, so we can just go, this is 3 moles, okay? And then we'll do the NiCl2, 150 grams of that, NiCl2. We'll
mhm.
get the molar mass of NiCl2. And that's 130 grams. So we can tell pretty quickly that this bottom one is the limiting one.
Mhm.
We don't actually need to get the number. You can just figure out, okay, it's smaller than that. So we know that one is limiting. So we start with this one, this value down here, and we go backwards. We're like, all right, well, how much calcium did we actually need?
Mhm.
Um, this theoretical yield of nickel would be, okay. There's so many questions here. I just don't know how you're supposed to make sense of it all. But 150 over 130, so that's 1.16 moles. So that's the general idea of how you figure out which one is limiting. This one is the limiting. The NiCl2 is limiting. We don't have enough of it.
Mhm.
So that answers that. How much excess reactant is left? Okay. So basically they're saying like, we know that Ca is an excess. So how much do we actually need? So you use the one that's limiting and you work backwards. You're like, okay, to produce 1.6 moles of Ni, use the mole conversion. 1 mole Ni is 1 mole Ca times 1 mole Ca is 40 grams Ca. So you're basically saying like, how much did I actually need? I didn't need 120 grams. I only needed 1.16 times 40, which is 46.4 grams. Okay. So you only need 46.4 grams, but they gave you 120 grams to start out, which is way too much. That's how much excess reactant is left. 120 grams minus the 46.4 grams, which is 73.66 grams.
Mhm.
Does that process feel clear?
Yeah, it does.
And that is actually one of the numbers on number
Yeah.
5, which feels good. Like, okay, maybe we got this, what are we at? 3 out of 5. But then we got to do what is the theoretical yield of nickel? What is the theoretical yield of nickel if only 42 grams? What is the percent yield? Okay. So they're saying, and we kind of already did this because we know the limiting one. We know that that's what it's like, okay, we've got just enough calcium and just enough NiCl2 to make nickel now. Like, you kind of reset. So you can start with that 1.16 moles of nickel and then keep going with its molar net mass. So there's 1.16 moles of nickel times, now we need the molar mass of nickel. And that is whatever it is,
58.6.
58.69. 1 mole of nickel, 58.69 grams of nickel. So we get that number, and that's like theoretical. It's like under perfect conditions, which never happens. If you think of baking, it's like, if it works out perfectly, you don't spill anything, all that stuff that happens. And we got 1.16 times 58.69. So that's the 68.1 grams of nickel. And that's the theoretical yield. If everything worked out perfectly. But the percent yield is you take the actual and divide it by the theoretical. So you go to do you have a lab by chance in this class?
Yeah.
So it's like you went to the lab and you actually did this, really well, but you only got 42 grams, but you're supposed to get 68.1. Your percent yield is this ratio. And this is fairly standard. I mean, you don't get really good percent yields unless you're in a perfect environment. That looks like it's the other number there. No, it's not. Why is that number there? Did I make a mistake?
Is it 46 over 68 over 1, or is it 42?
So it's
It's
telling you how much that they actually made, and it's like, how much should we have made? Which I don't understand, because if we got this one right, which is based on this one, unless let me look. Like you said, nickel's 58.69, 1.16 times 58.69. That seems about right.
Yeah, I don't know what's up with the answer key.
68.1-ish, and then
Maybe the 67.9 is supposed to be the 68.1 because it's like pretty similar.
yeah, that's true.
Like very like 1 point off.
Yeah. But that is like the thing to take home, from this problem is this percent yield, formula and how you do it and all that.
Yeah.
Not to get too bogged down by some of these numbers. Okay. Let's see how we're doing here. Number 6. All right, 60 liters of propane gas react with 80 liters of oxygen gas. What is the limiting reactant? So we got C3H8 plus O2. And I guess we believe that this is CO2 plus H2O again.
Mm.
So the C is the first one to balance because it's kind of in one spot. If you put a 3 there, that gives you 6 O's, 7 O's, and that's off here. So let's go to the H's. Like if we put a 4 there in front of the H2 to get 4 H's, that's 8 H's, 4 O's, 6 O's is 10 O's, 5 there to maybe get that to balance. All right, and then we start out with this 60 liters C3H8 times 22.4 liters C3H8 and 1 mole of C3H8. And then we gotta do, which one do we want to go to? We don't know.
We go to H2O, right?
It actually doesn't matter. You can pick one, but I was looking for information in the problem to see if there was like trending towards one. Let's go to H2O times 1 mole C3H8, 4 mole H2O. So back to the calculator.
Yeah, I got the same.
Great. So next thing we do it for is the 80 liters of oxygen gas. Really a similar calculation here, 80 liters of O2 times 22.4 liters O2 and 1 mole of O2. And a different mole conversion though. This time it's 5 mole O2 to 4 mole H2O. So this one, just looking at the numbers here, and that's where I think you maybe can do some things to decide this in advance. I'm not very good at that. I like to just do the calculation, but I think there's a way to kind of know what to look at this, that this other one is the limiting one. So the limiting one here is the O2. Limiting reactant is the O2. So we say, okay, well, since we're going to consume all of the 80 liters of the oxygen gas and we're going to make 2.14 moles of H2O, how many liters of the C3H8 did we actually need? So you always go from the limiting one, restart. You say, okay, I want to get to, I got 4 moles H2O to go to 1 mole C3H8, and then 1 mole C3H8 is 22.4 liters C3H8. And you figure out, well, how many did you actually need? In this case, we're going to get that number. And it looks like you only needed 12 liters, but you had 60. So 48 is the excess. Boy, I hope that's on that page there. And it is not. This is really frustrating. I wonder if the conversion is wrong. Or the equation. 3CO2, 4H2O. Yeah, the equation is okay. 502, 60 liters, C3H8, 22.4, 1 mole, 1 mole, 4 mole, 80. Okay.
We find the excess just by like subtracting.
The idea is that you know you're going to use up all of the O2 because it's the limiting one. So you figure out how much of one of the reactants you can make. Oh, how many liters of excess reactant are there? Not product. No, that's right. Sorry. So you start with O2. You say, okay, I'm going to make, how much water could I make? And then we got that. We say, okay, you make 2.14 moles of water. And then you say, well, how much C3H8 did I actually need? And that's where we're going backwards here with the mole conversion. And then you say, okay, well, I only needed 12 liters. Like if you put 12 up here, you will get 2.14 liters here is the point. And that's why this is such a powerful method, because it's supposed to be consistent whether you go one or the other. And since you only needed 12 liters, 60 minus 12 is 48 liters, which is the excess reactant.
Oh,
But let's check the other one here. How many milliliters of water are produced? So we know that 22.14 moles of water. 1 mole is 22.4 liters, and then we convert. That's not going to be right. We'll see. $47.9, 48. Huh. I don't see the issue here. Let me real quick try to do this calculation going to CO2 instead of the water, and why that would matter. But let me try to do that and see if we can, some of this can make some sense here. So 60 over 22.4 times 3 over 1, and then 3 over 5. Okay, so we still get 3 over 5, and then 3 over 5 times, I can't believe you'd have to go figure out both of them. I thought you could just do one or the other, but maybe that's the issue. The issue might be that we arbitrarily chose this one. There might be a reason that you have to choose the CO2 to do this correctly. Yeah, so if I do that, so you do get different numbers. All right. And is the answer 40? Is the answer 44?
yeah.
Okay, so if you go to CO2 instead of H2O, you end up finding that you only need 16 liters. So I'm guessing that's the issue here. Why would that be? 2.14, 2.14. Huh. Okay, so some thoughts here as we kind of close out is they're not telling you which one is the excess reactant, and you have to, I guess, decide that. And I don't remember why you can't just choose one. So, kind of our like here's some things to think about here is you need to obviously balance, write and balance the equation.
Yeah.
Okay, that's really important here. The second thing is is how, and this is something we teach for that TIG or someone else that really knows this stuff, how to determine which is the limiting reactant.
Mhm.
I'm sorry, the limiting product.
Yeah.
Because it shouldn't, I didn't realize that this mattered. Like I thought you could just go to either of them, but apparently in this calculation, it does matter. Like you use the two given amounts to go to one or the other. I didn't think it mattered, but apparently it does.
Yeah.
So I think that's what you want to determine. But then once you determine that, you always go back and figure out how much of the how much you actually needed.
Yeah.
And it's always less than what you have. And then you can do the calculations from there for that. All right, I do apologize. I